Hi guys, welcome back to Business Statistics. This will be the first video installment of modules 8 and 9 hypothesis testing, 1 and 2 sample procedures. This video is going to cover 8.1, but for these definitions I'm going to let you guys go ahead and find those in the PowerPoint slides. And really the only one that I'm going to talk through is going to be the 7 steps of the hypothesis test, because that's what we're really going to need. And I feel like you kind of learn the others based on kind of the example of what we do within the problems. Okay, so I'm going to let you guys write those in yourself. Yeah, let's go ahead and get started on example 1. I'll talk through the 7 steps first. So step 1, if you're writing along with me, or if you have it in front of you. Now these are your book definitions, and I'll kind of make allusions to what I think a more logical way to state that is, or a more logical kind of layman's way to approach it is. But so book definition of step 1: state the claim and identify the null and alternative hypotheses. Okay, so my definition of that would be pretty similar. So we're just going to be establishing our hypotheses, right? Another thing that you can kind of do along with step 1 that kind of happens outside of step 1, but nonetheless will kind of be the first thing that you do, is when you read through the problem, you want to kind of be noting the things that are notable, right, about this. So whenever you see something that looks like it might be mu, you see something that looks like it could be a standard deviation or an alpha level or an n, or anything like that you think is significant, or an interesting descriptor of the problem that you think leads you in a certain direction, just make note of that as you start the problem. Okay, so that's kind of like a step 0. Essentially, it's like reading through the problem and making notes of the important things of the problem. And then, step 1 of the hypothesis testing process is to create your hypotheses. So your H0 and your HA. Okay. Step 2 is establish or select a level of significance. Okay. A significance level. This is also known as your alpha level. Most of the time, not all of the time, but most of the time, a significance level will be given to you in the problem. And usually it's like 0.01 or 0.05. And if one isn't given to you, use your best judgment and decide on one before you start the problem. Step 3, identify the appropriate test statistic. That's absolutely right. So use the information from the problem to determine what type of formula you're going to be using. And then write that down. Step 4, formulate a decision rule for the test. So step 4, I like to draw a picture, establish the critical values, and create my decision rule. Okay, step 5 is the one that I think I have the most issue with the way that your book describes it. The book just says take a sample. Okay, that's for everything that we're going to be doing in this class, or for the stuff that is from the book, the sample has been given to us. So there's no real taking a sample. What this really should say, and what I'm telling you to kind of view it as, is use the information that you have and calculate a test statistic. Okay? So use the information that you have and calculate a test statistic. Then step 6 is compare that test statistic with your rejection rule from step 4 in order to make a decision based on the data and the calculated statistic. Okay, and then step 7 is interpret those results. That's what the book says, and the way that I would describe that is, give your managerial decision, give your within the context of the problem decision, give your real world decision. So in step 6, it's like, hey, excuse me. Step 6, it is like, hey, let's make our formal, like, hypothetical, or I shouldn't say hypothetical, but hypothesis-based conclusion. So basically, like, hey, let's go back to step 1, look at our hypothesis. What are we deciding to go with? That's step 6, okay? Step 7 is where we take that from like a statistical, probabilistic, mathy kind of statement, and we turn it into a real world statement. And we usually end up saying, we have significant evidence to suggest that, or we do not have significant evidence to suggest that, and then we state the aspect of the problem. Okay, so if you guys get a chance, re-listen to that spiel or whatever that I just gave you here. But I think it'll become more clear as we do a number of examples. Okay, so we're gonna go ahead and get started here. Another thing that I guess I forgot to mention is I apologize for my voice. I don't know if you can hear it now, but kind of the reason I've taken a little bit longer than normal to post these videos is because my voice was gone from like last Wednesday to pretty much yesterday. It's finally starting to come back. You can probably kind of hear it a little bit, but so yeah, if my voice goes in and out, I apologize for that, but we are going to get through it. We're going to get through it no matter what. Yeah, no matter what? Yeah, no matter what. Okay, sounds good. All right, let's get started on example 1. Testing a hypothesis using the critical value approach. The diameter of a particular precision ball bearing has a target value of 20 millimeters. Suppose the bearing diameters have a normal distribution with a standard deviation of 0.065 millimeters. When a shipment of bearings arrives, the consumer takes a sample of 25 bearings from the shipment and measures their diameters to see if it meets the target value, and finds the mean to be 20.15 millimeters. Perform this hypothesis test at the 5% significance level using the critical value approach. Okay, so the critical value approach is going to be kind of the approach that we use to solve all hypothesis testing in this course. We're going to do one example where I show you the p-value approach, and that's really just to get you ready for business analytics next semester or whatever semester you're taking it. Because more than likely, or for the most part of the business analytics course, you're looking through output and you'll be establishing whether or not you can make conclusions based upon p-values as opposed to critical values. Okay, so the critical value approach, I think, is a little bit less calculation intensive for the most part, and I think is a little bit more, I don't know, it might be a little bit more logical, but we're going to learn both, and you're going to mainly do everything with the critical value approach because it's the one that's easiest to calculate and takes like one less step than the p-value approach. Okay, so let's do what I had mentioned doing in regards to listing out the stuff that we know. Okay, so what do we have here? So it says perform this hypothesis test at a 5% level of significance using the critical value approach. So what kind of test are we using? Well, what type of thing are we trying to measure? The diameter of a particular precision ball bearing has a target value of 20 millimeters. It kind of sounds like a mean to me, right? Let's see. We have a standard deviation in there. Okay, the consumer takes a sample of 25 bearings from the shipment and measures their diameters to see if it meets the target value and finds the mean to be 20.15. So it looks like we have a mean here. Okay, because that's kind of a status quo population characteristic. We have a status quo kind of standard deviation, and we have an n value, n being the sample size. We have a sample mean, so x bar, and we have a level of significance, alpha. Okay, so a natural question that you'll have is, well, how do we know that 0.065 is a standard deviation of the population, so a sigma versus an S, okay? And it's kind of given to you in the verbiage of the problem, all right? It says, suppose the bearing diameters have a normal distribution with a standard deviation of 0.065. So it's kind of talking about the bearings holistically, right? And it's not, and we haven't even mentioned the sample yet, right? So at this point in the narrative, we don't know anything about a sample. So we know that it's that we're talking about like a population characteristic, because it says it says suppose. That's kind of a keyword, right? It's you're making an assumption. If we were talking about a sample standard deviation, it would have something to do with calculated, right? Or the sample it would literally specifically mention sample standard deviation, right? This has kind of a more airy kind of feel where it's like, oh, we're making this broad assumption. And when you're making a broad assumption, that's kind of, you're talking about, oh, well, we think that this status quo sort of thing, okay? So that's kind of how we know sigma, all right? So we kind of have what we want to get started. So I'm going to go ahead and list these things on the side. So we have mu of 20. We have sigma of 0.065. We have an x bar equal to 20.15. We have an n equal to 25. And we have a sigma given to us, a alpha given to us of 0.05. Okay, so that's kind of like our list of stuff. That's like our step 0, effectively. So now we get into step 1 of the hypothesis testing process. And this is when we're going to be establishing what our hypotheses are. H naught and HA. Okay, H naught being the status quo, so that's H null, the null hypothesis. HA being the alternative hypothesis. HA is kind of what we suspect to be the case, whereas H naught is what is kind of generally assumed to be the case. Okay? So HA is our suspicion. H null or H naught is the status quo. Okay? We always want to write in HA first. The reason that we do this is because then we can just make H naught the complement of HA. Okay, so let's figure out what our HA is. When a shipment of bearings arrives, the consumer takes a sample of 25 bearings from the shipment and measures their diameters to see if it meets the target value. Okay, so given the context of the problem, you want the ball bearing to be an accurate. You want it to be an accurate amount, an accurate mean. You want it to have an accurate size of 20 millimeters, right? You don't want that to vary too much, because effectively you're using this ball bearing inside of some machine, right? You know what I mean? Like, you're buying these for a purpose. They have to fit whatever you're using. And then thus, so you want it to be usable, right? So that's kind of like the real world application of it. So what does that suggest? That suggests that we want it to be equal to 20. It doesn't suggest that we want it to be, that we care if it's like bigger than or smaller than. We just want it to be equal. So we're testing to say, is this not equal? Because it seems like we have the suspicion that it might not be equal. So our alternative hypothesis is that mu is not equal to 20. And then conversely, H naught mu is equal to 20. Okay? So that's how it is to write our hypothesis, okay? And then 2, what is our alpha level? Okay, we just write that in. It was given to us. 3, what is the test that we're using? So we have a couple of options, or we have a couple of things to consider. Because the population parameter in question is mu, and not something else like P or sigma or something like that, because what we're studying here in our in our hypotheses is mu, we know that it's going to be one of two things. We know that it's either going to be a z-test about a population mean or a t-test about a population mean. How do we know that? We know that by looking at our table here. So this table can be found in the module 6 and 7 content. This is the table that you're going to get for the test. This is going to be very, very helpful to you. So if we look down here, we go down the table and we see variable in dispute. This could also say parameter in dispute. Okay, and we look for our hypothesis testing things. Our hypothesis testing things start at module 8. Okay, if we look at module 8, because we're still in one sample hypothesis testing, we only have 2 options that are included in mu, or that are about mu. So testing a hypothesis about a population mean with a known population standard deviation, that's our z-test, and then testing a hypothesis about a population mean with an unknown population standard deviation, that's our t-test. So this is the exact same concept that we worked on from 6 and 7, or from 7 mainly, but it's the idea that, like, hey, when we're given a population standard deviation, we use z. When we don't have a population standard deviation, or we just have an s, right, not a sigma, we use t. And then we can, like, look at these formulas and say, oh gosh, those formulas are like the exact same thing, except there's a z, and there's a t, there's a sigma, and there's an s. Okay, so for this problem in particular, we have a sigma, right? We have an assumed population standard deviation. So we know the formula that we're going to use. We know that we are using testing hypothesis about a population mean with a known population standard deviation, or a z-test, or you can call it a z-test about a population mean, and then just write this formula in. Okay. This video is getting long-winded already. Oh boy. Alright, so I'm just going to write z-test about a pop mean, and then that's just going to be z is equal to x bar minus mu over sigma divided by square root of n. Speaking of the length of this video, I'm not going to go into as much detail when I solve all of the other hypothesis tests. I mean, I'll try to go into some detail, but I don't want every video to be like a half an hour. But I wanted to fully explain out, like, all these steps and why certain things are the way that they are. So this video might be a little bit longer, but I think ultimately you'll appreciate that because it'll give you a decent understanding of how we're going to attack these hypothesis testing problems. Okay, so let me scroll down here. Okay. All right, so that's step 3. We've established this, and I also don't want them to run long because I don't know how long my voice is going to hold up. So I think by like the 3rd or 4th video, you're going to hear me like sounding like a frog. All right, number 4. Okay, so number 4 is what? Establish our rejection region and formulate a decision rule. Okay, so the first thing that I like to do is I like to draw a picture here. So we draw a bell curve. That's my best bell curve. And we're going to establish rejection regions. Okay, so we do this by looking back at our hypothesis. Well, we really do this by using step 1, step 2, and step 3. Okay, so we want to basically what we want to do is, one, we want to know how many tails does this have? Does this rejection region have? How many tails is our rule going to have? And the way that we do this is we look at step 1. We say, is this going to be less than, equal to, greater than, or sorry, less than, greater than, less than, or equal, not equal type deal. Okay. The only one that is two-tailed, is the equals, not equals scenario. Okay, that's what we have here. So we know that it's going to be two-tailed. If this was a greater than, less than scenario, it's going to be one-tailed. All right, and that tail is always going to point in the direction of whatever directional we have in HA. All right, you'll see that in the problems going forward, but that's the concept. Okay, so but for this one we have equal, not equal. So this is a two-tailed test. So I kind of just generically write in some tails there. And then these tails are called our rejection regions, RR. And then the area in the middle here is called our failed to reject region, FTR. Okay. Can you guess what the size of the rejection region is? The size of the rejection region is just the size of our alpha error. So basically this is the error that we allow to be wrong. Okay. So we're saying like 5% of the time when we run this test, we're going to be wrong. Okay, and so that is the area that we put in our rejection region. All right, so because we have 2 rejection regions, we have to split this up. So it's not going to be 0.05 and 0.05, it's going to be 0.025 and 0.025. And then our failed to reject region is 95. It's 95%. Okay, So these lines, what are these lines? These lines are going to end up being z values. So z critical values, in fact. So we have a z crit negative. It's called negative because it's to the left of 0. It's to the left of our proposed mu. And then we have z crit positive. Okay, and we just need to figure out what those are. So these are going to be the same number, except that one is going to have a negative sign, one is going to have a positive sign. So the way that we do this, and you guys might remember some of these numbers just based on the stuff that we just did in 6 and 7, but we had that list of numbers, 2.58, 2.33, 1.96, and 1.65. You can kind of use those numbers most of the time to figure out what we're going to be looking for. But just in case you don't have those memorized, let's go look at finding these in the table. Okay, so we're going to scroll down to our Z table, and basically what we're looking for is this tail. Oh, wrong one. This tail here. So our 0.025. So we want to find a 0.025 within the table. So we scroll down. Looking for 0.025. Okay, we passed it here. Scroll over. 0.025 right here, and then thus negative 1.96. Okay, and that's one of those numbers that we remember that we've used. All right, so our T crit negative is negative 1.96. If you did the same thing on the top end, you'd see that this is going to be positive 1.96. And then the idea is that then, so these are the rejection regions. This 1.96 is kind of this like line in the sand here that we've drawn. It's negative 1.96. Meaning if you cross into that, if you are to the right of that line, then you're in the rejection region. If you're to the left of that line, you're in the rejection region. So we just now need to write formally what that says. So we say reject if z calc, meaning the value that we're going to be calculating here in a little bit, is greater than z crit positive, that's equal to 1.96. Or reject if z calc is less than z crit negative, equal to negative 1.96. So I'm just going to repeat what I just said. So basically what we're doing in this statement is we're formalizing what we see here in this picture, right? We're saying if you cross over this negative 1.96, you're now in the rejection region. Or if you cross over this 1.96, you're now in the rejection region, right? So we're just formalizing that. We're saying reject if zcalc, our calculated value, is greater than z crit positive, which is equal to 1.96. So reject if it's greater than 1.96. That's just saying, hey, if you happen to be in this rejection region, we reject. Or hey, if you happen to be in this left-handed rejection region, we reject. We're rejecting the null hypothesis, effectively. Okay, so step 5. So that was step 4, all of it. Step 5 is let's calculate our value. So we're taking the formula from step 3, and we're just using the values that we have. So we call this zcalc. We say that that is equal to x bar 20.15 minus mu 20 divided by sigma 0.65 all over the square root of n, 25. And the number that we get is what? 11.54. Okay, positive 11.54. So this number happens to reside somewhere like over here, right? In terms of the paper. So it's greater than, we can see that it's greater than z crit positive. So we say, all right, reject, because z calc is greater than z crit positive, which is to say that 11.54 is greater than 1.96. Okay? And because I don't have the skills and the time to just write out long sentences, I'm just going to state step 7. So kind of state our conclusion, our managerial decision, our managerial conclusion. And that is just to say that the data provides significant evidence to support that the shipments do not meet the target value for the mean diameter of ball bearings, right? So our target value, we wanted it to be 20, and we're saying that we have significant evidence to suggest that these shipments, or not that these shipments, that the ball bearings that we would receive in a shipment are not actually going to be 20. Now, after we've seen this sample, after we have kind of run this test, saw the sample, run our statistic, we can see that, in fact, we think the mean is going to be greater. But remember, we're only really trying to conclude about the hypothesis that we've set out to establish, right? So our hypothesis is based on, step 1. And the thing that we have to run a conclusion on is based on step 1. So, yeah, we do have significant evidence to suggest that the mean is actually greater than 20. But what we set out to find out was, hey, is it different than 20? And the answer is yes. We have significant evidence to suggest that the answer is yes. Okay. All right, guys. I'm going to cut the video off here because I actually need to give my voice a little bit of a rest. But yes, I'm going to start and we'll do the next one on the p-value approach, and then we'll continue from there. All right. Thanks so much, guys. Let me know if you have questions.